Any questions so far? All right. Okay, so we're just going to redo what we've done. We've done a little of this about this before, but let's just do it again. So definition. So an ideal Q is primary if and only if one of the following conditions is true. So one, so all the zero divisors. Okay, let's do this. This is going to be in a ring A. All zero divisors of A mod Q are nilpotent. And the other condition that was equivalent to this, which we showed before, either I showed it to you or I put it in the homework. If this is in here, this implies that X is in Q or Y is in the radical of Q. Okay, so this is what it meant to be primary. Okay, so all right. So let me say there's kind of a quick lemma here. So lemma. So again, I just wanted to. So I said this. This is the proof of the fact. Of the fact from above. Let me see, where did I put that fact? Here. This is this thing. So if Q in here is primary, then this thing here is prime. Okay, so let's do the proof. Okay, so so A mod the radical of Q, right? So this is the same thing as A mod Q mod the nilpotent radical, but this is the reduction. So here we kill all zero divisors. So this was when we were doing all this stuff about nilpotents, right? But since all zero divisors are nilpotents, this ring has no zero divisors. This ring no zero divisors.
Wait, was that an assumption? All zero divisors are nilpotent, or is that just a fact?
That's what it means to be primary.
Okay, right. Yeah,
right. So yeah, so that's what that's the definition, and it's equivalent to this thing. So we did this. So this was an exercise when we first. This is what we did when we way back when we talked about nilpotents.
You're assuming one and showing two, right?
No. These I'm assuming that 1 and 2 are already equivalent.
Oh, okay, right. Okay.
I'm proving that the radical of a primary ideal is prime.
Got it. Good.
I showed a long time ago. Okay, by this I mean equivalence. Yeah, what's up?
In this statement of this lemma, what kind of thing is A?
A is a ring.
It's a ring? Okay.
Yeah, this is a ring. Sorry. A is always a ring for me. Yeah. So yeah, so it's just an ideal in a ring. That's primary. Okay. So and this is what I said, that this is called P primary, right? So this is radical Q primary. I already said that before. Okay, so let me show you the remark here. The converse does not hold. The converse does not hold. So this thing here, the radical of Q being prime, does not imply that Q is primary. Okay, so here is the counterexample. So here, let's just do this. So there's the drawing. Okay, so if you have an embedded prime here, well, if I take the radical of this, so this is I, and then the radical of I will just be this, which is prime. Okay, but let me kind of give it explicitly. So I looks like xy x squared, which is the thing that we had before, xy squared. Okay, and so the radical, so this is not primary. It has two primary components, right? It's not primary, but the radical of I looks like just the y-axis. So this is inside k of xy, and k is a field.
So when you write xy comma x squared is equal to x intersect xy quantity squared, that's the primary decomposition.
So this is the primary. So this is the ideal. This is its primary decomposition. So can you repeat your question?
No, I'm just making sure. Yeah.
Yeah. So this is the ideal. These are the two primary components of the ideal here, right? The two associated primary ideals. And the radical of this is just what it does is it smooths out this embedded thing and just becomes that axis there, the y-axis. Okay, so this is inside A2.
So I assume we could find it. It's probably easy to see, I guess, an x and a y that when you multiply x times y to the n, you'll never be back inside there. Is that why it's not primary?
You can find an x and y. It's not primary because the radical, because it has two primary components. But yeah,
Okay.
explicitly you should. Yeah. So I guess what you could do is you could find a zero divisor. Let's look at this. K of xy mod I. Okay, so let's look at this. So this looks like K of x. Well, yeah, here's a good example. So this is this xy x squared. Okay, so xy bar is a zero divisor that is not nilpotent.
Got it.
Okay, so it has zero divisors.
Can I ask a quick semantic question about the dot and the line? You say like the dot is embedded in the line.
Yeah.
But usually I think of embedded as inside. Is that kind of because of the reverse inclusion qualities of ideals, the way that they work? Is that kind of?
Yeah, it's the reverse inclusion of ideals, but it's for the radical ideal. So here, note that the radical. Okay, so we have two primary ideals, right? We have, okay, so we have Q1, which is this big line, and then we have Q2, which is the fat one. So Q1 here is X, Q2 is XY squared, okay? And so the radical, of Q2 is just this maximal ideal, and it's contained in, it contains, the other way around, it contains the radical x, which is the radical of Q1, which is Q1, right? Okay, so what this is saying is that really like as a topological space, V of Q2, the underlying topological space, is contained in the underlying topological space of V of Q1.
Awesome. Okay, I figured it's something. It's like when you draw the fat dot, it's like, well, that's too fat to be inside there, but but that's why it goes opposite. Yeah.
Yeah, so the underlying topological space of a scheme only knows about radical ideals, right? It knows nothing about primary ideals. I mean, it knows, I mean, to the extent that it doesn't know anything about the embedded primes, right? So, yeah.
That's like what Grothendieck wanted to fix. I don't really know what I'm talking about when I say that, but is that? I don't know.
No, that's correct, right? The idea is like we want to keep track of nilpotence and multiplicity, right? So we want to keep track of order of vanishing. And this is why we work with the ring instead of topological spaces like this.
Cool.
The rings, the algebraic part of algebraic geometry is what allows you to keep track of things like embedded stuff. Okay. Okay. So okay, so the other thing that I wanted to say is, so let's give an example of primary ideals. So in Z, the only primary ideals are the things that look like P to the N for P of prime. Right, and this is the same thing. So note that P to the N is the same thing as P to the N. Okay, so this is why maybe you would think that like powers of primes ideals are primary. But here's an example. So here's a counterexample. So not every power of a prime ideal is primary. Okay, so let me look at this example here. All right. Let me find it. So it's in the ring. So we have to take the ring A, looks like a field, X, Y, Z. And then you do Z squared minus XY. Okay. And then what do we do? So I have to pick this example. So I think it's like I take X, Y. Yeah, that's what I do. Okay, so then we do this ideal. So let's do P. Let's do X bar, Y bar. Okay, so this is prime. Okay, so let's do A mod P. So, oh, sorry, this is not X bar, Y bar, X, Z. Let's do Z. Okay, so if we kill X and Z, right, then the whole ideal goes away. And then this thing is just isomorphic to K adjoining Y, which is a domain. Okay, and so now let's do P squared. Okay, so P squared is the ideal X bar squared, X bar Z bar, Z bar squared. Okay, so this thing contains, so this contains, so this ideal contains X bar times Y bar, right? Since it's equal to Z bar, right? But you know, Y bar to the N is not an element of P squared for any N. Okay, so here we're using the property that, so neither is X. So here we're using that, so here we're using the property that, and this is kind of a weird thing about this. I always get mixed up. So for Q primary, okay, let's do it like this. I'm just using the definition of primary again. So if Q is primary, right, if and only if F, G, and Q implies F is an element of Q, or G to the N is in Q for some N. Okay, so this is what we're applying. And so here we have X times Y. This is in P squared, right? But you know, they're not in X to the N. You know, they're neither of them are in neither of them to a power. Or let's see, hold on. So X is not an element of Q. So here we have X is not an element of Q. Not X is not an element of P squared, and Y bar to the N is not an element of Q for n for all N greater than or equal to
Q will
1.
also be P squared.
Uh,
Right there, Y to the N is not an element of.
oh, sorry, P squared. That's P squared. Yeah, that's correct. Right. The weird thing about the reason I always get tripped up in this definition. Okay, so here's a good exercise, right? If you have you've never done this, is check that this definition is actually symmetric. Definition. Meaning that, you know, like that, you know, you could have done this, you could have done this either way. Or for some N, or G is in Q. This is the same thing as this condition. Right? Okay. By the way, right, this is the same thing, saying that a power of this is in this, that's the same thing as the radical ideal definition that I gave before. Where is it? Here, right?
In
Okay.
your example, you said X times Y was Z or something like that. I'm sorry to take you back to that. I was just
Yeah, no. These are good questions. Keep interrupting me. Yeah. X times Y is Z squared.
Yeah, how?
Because we imposed it. We forced it.
Oh, yeah. Okay, that's 0.
By the
Yeah.
way, this thing is a really good example for a lot of things. So like this is a great example of not a non-UFD.
When you were making that, is that kind of you're like, I want X, Y to be Z squared? Is that kind of
Exactly.
Okay.
You just
Start
cheat,
that thing.
right? It's like I need a ring that like is not a UFD or something, so that you can have you know. And this is like a very good example of.
So Z squared is Z times Z, and it's X times Y, so it's not
Exactly.
unique, and that creates this situation. Okay.
Yeah. So you kind of like cheat, right? It's like I'm not good at naming non-UFDs, so I make one.
I have a question.
Yeah.
We're assuming all these rings are commutative, right? So why is this thing that you're asking us to check? Isn't that like a given?
What? Sorry. What am I asking you to check this thing?
Yeah.
I mean, this relationship right here, F times G is in Q only if G times F is in Q.
Yeah, because all of our rings are commutative, right?
Exactly, true. Yeah. But it looks like this could be a crap definition. Right? Couldn't I have given you like some sort of bogus definition that doesn't work? It looks like, so the issue with this definition, it looks like, is that the rings are commutative, but this relationship doesn't seem to be commutative, right? The condition on the right-hand side, it's not a priori commutative,
Okay.
right? But it is. Right, that's what I'm saying. Is that this looks like it's not well defined, but it is. Okay, so I need to give you the exercise. for the day, and then we'll continue this next time. So next time what we're gonna do is we're gonna prove these theorems here. So this is the big one, and then I guess and I guess along the way to prove this, I'm gonna show you how to get the primary decompositions. So via the operation of saturation. Okay. So so the exercise, so the quiz problem. Okay, so consider the ideal I, which is generated by, okay, so y squared plus yx plus x squared, y plus x, and y. Okay, so which of the following are minimal Robner bases? Okay, and then this is for the term order, y bigger than x. Okay, so G1 is yx, G2 is yx squared, G3 is y plus xx, and G4 is y plus x, y. Okay, and then after you do that one, do this. So then do this, which are reduced. Okay, so that's the problem. And that's all I have to say. So I'm going to stick around as usual if you guys have questions. Other than that, you guys should peace out.
Thank you.
You're welcome.
Thank you.